Welcome to this video screencast recording of a very simple refrigerant cycle for an air conditioner represented as SysML activity diagrams driving a state machine in Cameo Simulation Toolkit for MagicDraw SysML or the Cameo Systems Modeler Enterprise Edition. This video only shows the activities and state machines. For more information about the underlying SysML model, please visit also this accompanying slide trail. Here we are inside MagicDraw or Cameo with an activity diagram for driving the state machine and the monitor windows for Cameo Simulation Toolkit showing. You can see that we can navigate the block model and value properties, including their values, and substructure for our simple domestic air conditioner model. There are also some breakpoints set, especially on exit pins for the actions and on state machine transitions. The state machine is driven by the activity. Let's look very quickly at the state machine. The state machine has 4 states corresponding to the refrigerant cycle. There are 4 transitions for compress, condense, expand, and evaporate, driven by corresponding signals. Returning to the activity, we see that we have to enter the refrigerant cycle somewhere, which we do by creating some refrigerant vapor before the compress part of the cycle. The activities behind the core behavior actions representing each stage of the cycle are mostly just stub activities representing the transformation. For example, here we see low pressure refrigerant vapor come in, super hot refrigerant vapor goes out. The activity sends a compress signal which will be received by the state machine. There's no actual modeling of the heating of the super hot refrigerant vapor in the activity yet, but that could be easily included for a realistic model. Let's look next at the condense activity. We have super hot vapor coming in of type refrigerant vapor. We have condensed refrigerant liquid coming out. So there is a transformation of the type. This has been represented here by a create object action. It could have been done perhaps using a reclassify object action. For some reason I could not get that to work in Cameo Simulation Toolkit. So instead I just have it's sending a condense signal, which will trigger the state machine transition, and it creates a new object, a refrigerant liquid object. Next, we look at the expansion behavior. This represents a simple thermal expansion valve. Now, this stub activity simply sets fixed values for the ratio of vapor and the ratio of liquid. Now, normally this would incorporate information on the pressure from a sensor which is attached to the top of the evaporator. A fleshed out model would leverage this pressure information for performing a realistic calculation. For this stub activity, the pressure is simply discarded. Now, there's a subtle matter here concerning coordination of the activities. That control flow from the condense action to meter sensor bulb pressure does not represent some kind of physical flow. It's coordination of the execution of the actions. The control flow ensures the correct execution of the actions for provision of the condensed refrigerant liquid and the metered pressure. Let's look now quickly at the evaporate activity. Here we have another complete transition from refrigerant to refrigerant vapor, assuming that the evaporation is complete. So it just sends an evaporate signal, which will be received by the state machine and cause a transition there, and a new refrigerant vapor create object action is used rather than transforming the type of the incoming refrigerant. Okay, let's simulate the system in Cameo Simulation Toolkit. It's always worth adjusting the animation speed, and you may wish to set auto open diagrams to true under the simulation options and the play button to start. Now, although this simulation was started from an activity that is an owned behavior of its owning block, which acts as context, the classifier behavior was the state machine. So the state machine will automatically commence first. There's actually a breakpoint on the initial transition. So if we hit resume, we move to the low pressure, low temp vapor state. There's a breakpoint on the entry pin to the compressed behavior. If we resume on that, move into this stub behavior, you see that it in fact does not do any calculation. It's merely a stub. It does, however, send a compress signal. That signal is then received by the state machine. There's a breakpoint on there so we can see it. And resume again will take us to the next state, superhot vapor. Okay, if we move past the breakpoint on the output pin for the compress action, and then past the breakpoint on the input pin for the condense action, we move into its corresponding activity. This also does not perform calculations. However, it does send a condense signal. A breakpoint on the transition for condense catches it. We can move past that into the condensed liquid state. And then it creates a new object of kind refrigerant liquid. So there's a transformation from refrigerant vapor to refrigerant liquid. Now, as I remarked before, this may be possible with the reclassify object action. However, I couldn't get it to work in Cameo Simulation Toolkit, and I'm not sure at the moment whether it is in fact supported. So I've chosen to use a create object action. Okay, so as before, we hit a breakpoint on the output pin. However, this time something else happens. We call that control flow, ending at meter sensor bulb pressure. It has nothing to do with physical flow. It's merely coordination of the actions. And you can see that it ensures that a new pressure and new refrigerant liquid are available for the next action. Now, this expand activity does a little bit more. It's still, however, only really a stub. It sends first an expand signal. One could perhaps choose to send this at the end of the activity. I've decided to send it here first. So move past the breakpoint again to reach the state expanded, low pressure, low temp mix. Now, the equilibrium pressure from the sensing bulb, which would typically be at the top of the evaporator, which is in thermal equilibrium with the top of the evaporator, is in fact not used in this stub activity. It's just thrown away using a flow final. In a real system, old mechanical style, it would adjust the diaphragm of a poppet valve that then controls the mix of liquid to vapor. But for the moment, the stub activity just throws it away. Okay, so the activity here uses old school, low level, add structural feature value actions. You could do it with opaque scripting, or even fancier with the action language for foundational UML ALF. In any case, first the state of the refrigerant is set to mixed. Note that the sense in which the term state is used here is just for a value property. You could have actual states for the refrigerants. At the moment, we only have states and a state machine for the entire cycle. Using completely arbitrary values, the ratio of liquid is set to 0.9 and the ratio of vapor is set to 0.1. So we have a condensed refrigerant liquid coming in, and we have a refrigerant that is a mixture of liquid and vapor coming out. Now there's a breakpoint on that output pin from the expand action. And one of the nice features of Cameo Simulation Toolkit is if you hover your mouse over the little pin, you can see the values within the object. So there we have the state mixed and the ratio of liquid 0.9, ratio vapor 0.1 that was set by the action. Now you can actually use this hover feature to track the transformation of objects. There we have the values as it went into the compress action. We have the values as it comes out as refrigerant vapor there. We have values for it going into the condense action. And if you hover over the actual action itself, you get values within it. And you can, of course, also see variables change in the variables monitor, but this model, in fact, doesn't have many variables to set. All right, so moving past our breakpoint and into the evaporate action, this is another transformation type activity. It sends an evaporate signal, which, as before, is caught by the state machine breakpoint, was moved to the next state. Low pressure, low temp vapor, and then it creates a new object of type refrigerant vapor as output. Okay, we've gone once around the refrigerant cycle. Let's increase the animation speed and go through the entire cycle again a little faster. Okay, in the compress, it simply sends a compressed signal, causes a state transition to superhot vapor. Out comes our superhot vapor, goes into the condense activity, which performs a transformation to refrigerant liquid. We now have condensed refrigerant liquid, which in principle would be modified through the expansion valve according to the pressure, but we've just skipped that step. We have a set value for the ratio of vapor to liquid that then goes into the evaporator and undergoes a transformation, hopefully, to 100% vapor. So that's the end of our state machine cycle, and that brings us back again to the beginning of the cycle, and that would keep going around. All right, that's it. I hope you enjoyed it. I hope you agree it's a nice little demonstration of the way activities can drive a state machine. I hope you agree that Cameo Simulation Toolkit is very cool. Now do also look up the nice little slide trail that accompanies this tutorial. There are a lot of good tips there about how to organize your model, how to do block modeling, and how to diagram. And of course, if you want to learn how to use SysML truly effectively for model-based systems engineering, contact Webel and ask us about our unique comprehensive course in SysML and model-based systems engineering with Magic Draw and Cameo.